The last chapter. Chapter 14. We're going to mention what's in 15 and 16 because you kind of got to have the idea of that. But the last chapter where we're actually going to work problems is 14. It's so exciting. So 14 is about dynamics. And if you go to PhD school, you probably will take a whole semester of just statics and then a whole semester of dynamics. So we're doing, basically the whole semester of statics minus a few days where we're doing dynamics. The point of dynamics is about a path. So we've been looking at individual points, and now we're going to look at a path. And we'll talk about what that means more here in a minute. The Force is with you, but you are not a Jedi yet. All right, so we already talked about one way we're going to use dynamics, and we're actually not going to do much of this here in this class because this is total derivative thing function chapter 16. So we'll talk about it more when we get close. But when demand moves out, we normally just go, hey, we were at A and now we're at B. What happens? Well. And that's comparative statics, right? A and B, if we just look at A and B, that's comparative statics. Dynamics says, how do we get from A to B? Well, what happens, of course, is we were here, which means that shift in demand creates a shortage, right? And businesses respond to that shortage. Yes? And how do they respond? Well, we always say, well, they raise the price, and we kind of draw it like this as that's what happens. Well, maybe that's not what happens. Maybe we start here at A, and maybe they just jack the price straight up this way, and then they put the price over here, and then it goes over here, and then it goes over here, and then, wait a second, we're going the wrong way. Okay? So depending on what the adjustment mechanism is, you can have stable supply and demand or unstable supply and demand. And we always assume an adjustment mechanism that makes it stable, but you certainly could have a stock market bubble in a regular old supply and demand market, right? If you understand the dynamics of it. Okay? Now, particularly what we're about to talk about is taking integrals, integration. Let's think for a second. So here's x and y, right? And there's a line, and let's say that the slope of the line is 2. Just 2. It's constant 2. Okay? Everybody with me on that? Well, if the slope is a constant 2, I know that straight lines have equations that look like that. I know that that means that there's really an x kind of implied in there, and that b in the traditional way of doing that is down here. And if I pick a point, I pick that point right there. I pick that point. Okay? At that point, I know that, x is, right? X is something and y is something. If I know what x and y are, I can figure out what b is, right? If I know where this point is, it has a coordinate, right? I can find that, and I can go back and find b. So we often say to everyone, well, look, you need 2 points to define a straight line. Well, that's wrong. That's one way to find a straight line. Another way to find a straight line is to know one point and the slope. Yay? Okay. So if I know one point and the slope, I can work backwards and find out what the equation for the line is. I can take this number 2 and turn it into y equals 2x blue. Okay? If I have that, if I have a half a hyperbola here, the slope at that point is 2x, whatever x is. So if x is 5, the slope here would be 10. Okay? And we can draw, remember, we can draw a line that's not really a good one, but a line that's tangent to that point right there. Okay? Yes, and we're measuring the slope on the tangent, but this is 2x. And down here there's a b. Well, if this is a 2x, yes, I know the function that comes from y equals x squared, and then the equation's going to have a, and I can work backwards and get that. Okay? So again, if I know a point, which I do, it's 5 and whatever this is, and I know the slope, I can actually find the equation for the line. It's like a miracle or something. Okay? All right. So I know that the derivative of x squared dx is 2x. And I know from back here that 2x, so we're going to do something called integration, and we have a big funny looking shape like that. Okay? And what it does basically is take the derivative and go backwards, which in a sense means it's adding things up. It's like a summation, a very small, it's kind of a way more advanced version of sigma, the summation sign. But back to that in a second, or maybe longer than a second. So we have an integral, right? And if we have fx, our first derivative, we always then write a dx on here if it's x we're worried about. So we say the integral of fx dx is the original function f of x plus c. And that c is the constant of integration. Okay, why is that c there? Well, yeah, this. So if I say y equals 3x squared plus 6, f of x would be 6x, right? Because that turns into a 0 and that turns into 6x. So if I take the integral of 6x dx, I'm going to get 3x squared plus something, but I don't know that it was 6 originally. I'd have to have some way to go back and find out that that was originally a 6. For example, I have to know a point on the function, right? A point on that line, a point on the line, and then I can go back and figure out what that is. Exciting. Yes, it's exciting. It's exciting. So, for example, just like we had a power rule for derivatives, we have a power rule for integrals, and it's going to be the opposite. So x to the n dx, the integral of x to the n dx, is 1 over n plus 1 x to the n plus 1 plus c, that constant of integration. And again, integral of x cubed dx equals n plus 1, right? N plus 1 is 4. 1/4 x to the n plus 1 is 4 plus c. Well, the integral of x, the derivative of 1/4 x to the 4th dx is x cubed. We bring the 4 down, times 1/4 is 1, and it's x cubed. Okay? So integration is backwards differentiation. Now you think, well, I can do differentiation. Integration can't be hard then. Integration is way harder. Integration is so difficult that when you take calculus, your calculus book will have real calculus, not math econ, but you go take like engineering calculus. You will have pages and pages and pages of pre-solved integrals in your book usually. And there are books and now online things where you can go look up integrals. If you've ever watched The Big Bang Theory, there's an episode where they're developing an app, and it's something related to integrals, which is a later chapter in this book, which is differential equations, right, which is chapter 15 in this book. So they actually build an app, or try to build an app. It's a comedy show, right? But they try to build an app where you snap a picture of a differential equation and it looks up the answer for you in a table of, okay? So finding the value of an integral could be way harder than finding the derivative. Finding the derivative is usually much easier. Okay? So, for example, that is just this. And that is just that. Okay? So it's the opposite. If you think about these things, it's just the opposite. We can do a lot of the things we do in derivatives, we can still do. So that's going to be equal to, we can split that up. Right? We have an addition rule. If we add two things we're adding up, we can split them apart and find the derivatives of them all cleverly split apart. That works just fine. Okay? If we have the integral of k dx, yes? So we have a constant. That's kx plus c when we're done. Okay? If we have a constant, we can move it outside. So the integral of kx dx is k times the integral of x dx. Yes? It's very exciting. So we can move that out. We can do all of this stuff that we did before. All right? The integral of e k to the x dx equals the integral of k to the x over k plus c. Because remember, the derivative of e to the kx is k e to the kx, and the two k's would cancel out, and yeah. Okay. I can tell you're excited. Excited? Yeah. There's a chain rule that applies in integrals. Okay? So you have an integral, again, fx dx can equal u du dx dx. Is that exciting? Yeah. 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 No? Okay. Yeah. No? Okay. So if you have the integral of 3x cubed plus 2 dx, you can make that u, so that u equals x cubed plus 2. Yes? And then you can do stuff. Okay? So du dx of that equals 3x squared. Okay? Yeah? So this is 4 times u du, because that's u, and that's u, right? Is 4u du. Okay? And then you're going to put it back in, and we're not going to keep doing this whole thing, because why? But you see, we can simplify it. That's what you do in integrals. You look for something you can do to simplify this sucker. Now you could just, I mean, in the real world, we would just multiply those two things together. But what if this is, something's to the, that? Now you've got a mess, and you've got to figure out, yeah, and you don't want to do that. Okay? Trust me on that. Trust me. Trust